Section: Introduction. In this section, we introduce a scenario similar to taking an exam where we rely solely on our reasoning without any external help. When faced with a tough problem, we might first attempt an answer, gauge our confidence, and adjust our reasoning until we feel sure. While confidence doesn't guarantee correctness, it often serves as our only guide in the absence of feedback. In such situations, we tend to focus on boosting our confidence or reducing uncertainty. In machine learning, we measure uncertainty using entropy, which indicates how concentrated or spread out a probability distribution is. Language models generate distributions over tokens, and lower entropy suggests higher confidence in predictions. However, many current methods for enhancing language models still depend on external supervision, rewarding them based on their accuracy against true labels. This reliance can be impractical in real-world situations where supervision is limited or absent. To tackle this issue, we propose RENT, which stands for Reinforcement Learning via Entropy Minimization. This is a fully unsupervised reinforcement learning approach that enhances reasoning performance by using the model's own confidence as a reward. We define this reward as the negative entropy of the predicted token distributions, which is straightforward to compute and does not require true answers. Our analysis shows that not all parts of a response are equally important for performance. We find that minimizing entropy for tokens towards the end of the reasoning process, especially those that represent the final answer, is most strongly linked to improved accuracy. In contrast, early tokens have little impact. This indicates that as we near the final answer, we increasingly depend on our confidence, making it crucial to encourage confidence in these final steps. We demonstrate the effectiveness of RENT across various reasoning benchmarks, including GSM-8K, MATH500, AMC, AMY, and GPQA. Our method works well across different model families and sizes, consistently enhancing performance. Next, we discuss related work on confidence and calibration. Confidence measures indicate how certain a model is about its output being correct. To evaluate this confidence, we also need to consider calibration, which assesses how well these confidence levels align with actual correctness. As language models are increasingly relied upon for significant decisions, providing a trustworthy confidence measure becomes essential. Researchers have developed various metrics to assess confidence in deep learning models, some requiring access to model weights and others estimating confidence through prompting. We also touch on test time adaptation, where a model is updated using data from the test distribution without ground truth labels. This aims to improve performance when there is a shift in distribution between training and testing. Techniques for adapting without labels include normalization methods that adjust feature statistics during testing. The most relevant work to ours is TENT, which minimizes entropy on model predictions at test time, assuming that well-adapted models should have low entropy predictions. In the realm of unsupervised reinforcement learning, we train agents using intrinsic rewards like novelty and entropy, allowing skill development without external feedback. Previous methods have focused on maximizing entropy, while we minimize it by reinforcing high-confidence outputs, leading to better reasoning performance for language models without needing external supervision. Finally, we explain that the goal of reinforcement learning is to train a policy that generates actions to maximize expected rewards. In modern language models, the policy is the model itself, and the actions are predictions sampled from a vocabulary. We frame this as a one-step RL problem where the model generates predictions and receives rewards. Traditionally, rewards are based on matching the ground truth answer, but our work emphasizes unsupervised reinforcement learning, which does not rely on external supervision for rewards. Section Summary. In this section, we introduce RENT, an unsupervised reinforcement learning method that enhances reasoning performance in language models by using the model's own confidence, quantified through entropy, as a reward. We demonstrate that minimizing entropy, particularly for tokens near the end of the reasoning process, significantly correlates with improved accuracy across various reasoning benchmarks, without relying on external supervision. Section: Group Relative Policy Optimization, GRPO. In this section, we discuss Group Relative Policy Optimization, GRPO, a reinforcement learning method that focuses on relative performance instead of absolute performance. Rather than simply maximizing the reward of our current policy, we assess it against a set of baseline policies. This approach enhances learning stability, particularly in environments with noisy or unsupervised rewards. We denote our current policy as pi, and our reference policies as a group, which we label as pi_1, pi_2, up to pi_k. The GRPO objective involves calculating the expected reward from our current policy and comparing it to the average reward from the reference group. This comparison provides a learning signal based on how much we improve relative to these baselines. Next, we introduce the concept of entropy reward. For a given input, our model generates a response consisting of multiple tokens. For each token, we produce a probability distribution over the vocabulary, which reflects our uncertainty in predicting the next token. We measure this uncertainty using entropy, which we calculate by averaging the entropies of all tokens in the response. Higher entropy indicates more uncertainty, while lower entropy suggests more confidence in our predictions. We use the negative entropy as a reward signal, encouraging our model to produce more confident predictions. Our learning objective then becomes maximizing the expected reward across the data distribution, allowing the model to generate responses with lower uncertainty without needing external supervision. In our experimental setup, we train our model using reinforcement learning on various datasets independently. We evaluate our model on several benchmarks that assess reasoning abilities in large language models. These include GSM-8K, which has nearly 8,800 grade school math problems, Math 500, a subset of competition math problems, AMC, which consists of modified high school competition problems, AME 24, a prestigious high school math exam, and GPQA, a dataset of advanced multiple choice problems in science. We use the same dataset for both training and evaluation to facilitate test time adaptation, ensuring that we do not rely on ground truth answers. To demonstrate the versatility of our method, we conduct experiments across a variety of models with different parameter counts, including Mistral 7B, Instruct V0.3, and several versions of Quen models. For our RL optimization, we implement GRPO with a specific learning rate and the Atom optimizer, adjusting batch sizes and sampling parameters as needed. We provide a comprehensive list of hyperparameters in the appendix. Section Summary. In this section, we describe our use of Group Relative Policy Optimization, GRPO, to enhance policy learning by comparing the current policy's performance against a set of baseline policies, which stabilizes learning in noisy environments. We also outline our experimental setup, detailing the benchmarks and models used to evaluate the reasoning capabilities of our approach, ensuring a comprehensive assessment across various datasets. Section: Main Results. In this section, we present our main results. We illustrate the performance of our models before and after applying entropy minimization on various datasets, including GSM-8K, MATH 500, AMC, AIME 24, and GPQA. It's important to note that all models, except for the math models, are instruct models. We observe that entropy minimization enhances the reasoning abilities of large language models across different families, sizes, and benchmarks, without needing external supervision. For math models like Quen 2.5 Math 1.5b and Quen 2.5 Math 7b, the base model often struggles with following instructions, resulting in low initial scores. Thus, the improvement from entropy minimization is substantial. Even for models that are already good at following instructions, we still see notable performance gains. We also address a common issue in reasoning benchmarks where models can lose points simply due to incorrect answer formatting. For instance, GSM-8K requires answers to follow a specific format, and Math 500 expects answers to be boxed. We have invested considerable effort in creating prompts that encourage correct formatting and in developing parsers to extract answers effectively. This raises the question of whether our method, RENT, merely helps models format their answers correctly rather than enhancing their reasoning skills. Our findings show that models trained with the rent reward outperform those that only receive a format reward, which simply gives a binary score based on formatting. While there are instances where our method performs similarly or slightly worse than the format reward, we expect that unsupervised reinforcement learning methods may not always yield significant improvements. However, across various datasets and model sizes, we consistently observe better performance with rent, indicating that the model is genuinely learning to tackle complex problems and enhance its reasoning abilities. We also explore the relationship between entropy and accuracy. Our analysis shows that as the model's confidence improves through rent, its accuracy also increases, confirming our hypothesis that boosting confidence leads to better accuracy. In comparing our approach to TTRL, which uses majority voting as a reward, we find that both methods perform similarly on several datasets. However, rent significantly outperforms TTRL on AMY, highlighting that rent provides a stronger learning signal for challenging tasks where majority voting may not be effective. We present qualitative samples from GSM-8K and AMY, which confirm that our model learns meaningful reasoning skills through entropy minimization, rather than just focusing on formatting or engaging in reward hacking behaviors. Lastly, we investigated which response tokens are most effective for minimizing entropy. We evaluated several strategies, such as selecting tokens from the last chunk of a response or the last 10 tokens. Our results indicate that the last chunk strategy shows a stronger correlation between negative entropy and accuracy compared to the first chunk strategy. This suggests that minimizing entropy over later tokens in the response is more beneficial. Additionally, our findings indicate that simply minimizing the entropy of the final answer tokens is not enough, as their confidence may not accurately reflect their true accuracy. Section Summary. In this section, we demonstrate that entropy minimization significantly enhances the reasoning abilities of large language models across various benchmarks, even without external supervision, and that it leads to improved accuracy correlated with increased confidence. We also show that our method, rent, outperforms simple formatting rewards and majority voting in challenging tasks, confirming that the models are genuinely learning to reason rather than just format their answers correctly. Section: Limitations. In this section, we acknowledge that unsupervised learning has its limitations when compared to methods that utilize external supervision. Consequently, it is not surprising that our approach does not perform as well as those that have access to accurate answers. We recognize that our model can sometimes be confidently incorrect, which is a common issue with language models. These calibration errors can lead to significant failures in our method, making it risky to use such an unsupervised approach in real-world applications without proper safeguards. However, we have observed that, in practice, confidence tends to align with accuracy, and performance improves when we consider confidence alone. This suggests that, despite some instances of overconfidence, our model is generally well calibrated.